What would happen if you fell into a black hole?
Section 51.
Section 51.
Section 51.
Hi everyone, what's up? I am GH aka DOSGeek back with Section 51. Black holes are without question some of the strangest places in the universe. So massive that they hideously deform space and time, so dense that their centers are called points at infinity, and pitch black because not even light can escape them. And here comes the big question. What would happen if you fell into a black hole? You might expect to get crushed or maybe torn to pieces, but the reality is stranger than that. The instant you entered the black hole, reality would split in two. In one, you would be instantly incinerated, and in the other, you would plunge on into the black hole utterly unharmed. The black hole is a place where the laws of physics as we know them break down. Einstein taught us that gravity warps space itself, causing it to curve. So, given a dense enough object, space-time can become so warped that it twists in on itself, burrowing a hole through the very fabric of reality. The gravitational field becomes so strong that not even light can escape, rendering the region where the star used to be profoundly dark a black hole. The outermost boundary of the hole is its event horizon, the point at which the gravitational force precisely counteracts the light's efforts to escape it. Go closer than this and there is no escape. And as you go deeper into the black hole, space becomes ever more curvy until, at the center, it becomes infinitely curved. This is the singularity. Space and time cease to be meaningful ideas, and the laws of physics, as we know them, all of which require space and time, no longer apply. What happens here, no one knows. Another universe? It's still a mystery. But considering our knowledge in sciences, some scientists tried to describe what would happen. So if you were to take a step into a black hole, your body would most closely resemble toothpaste being extruded out of the tube. As you accelerate toward the event horizon, you would stretch and contort, and the closer you get to the horizon, the more you appear to move in slow motion. Because when an object crosses a black hole's event horizon, its outer boundary, or point of no return, the same physics that causes Earth's ocean tides begins to take effect. Gravity's strength decreases with distance, so the moon pulls on the side of the Earth closer to it a bit more vigorously than the side farther from it, and as a result, Earth elongates ever so slightly in the direction of the moon. The land is sturdy, so it doesn't move much, but the water on Earth's surface is fluid, so it flows along the elongated axis. That's the tidal interaction. Rising tides are about as calming a scene as there is. A human towing the line of a black hole? Not so much. Near a black hole roughly the size of Earth, tidal forces are magnified off the scale. Swan diving into one, the top of your head would feel so much more gravitational pull than the tips of your toes that you would be stretched longer and longer. The British astrophysicist Sir Martin Rees coined the term spaghettification, which is a perfectly good way to put it. You eventually become a stream of subatomic particles that swirl into the black hole. Because your brain would dissociate into its constituent atoms almost instantly, you'd have little opportunity to soak in the scenery at the threshold of a Earth-sized black hole. However, if you're dead set on visiting a space-time singularity, some researchers recommend going big. Bigger black holes have less extreme surfaces. Because if you had a black hole the size of our solar system, then the tidal forces at the event horizon are not quite that strong. So you could actually maintain your structural integrity. In that case, you would get to experience the effects of the curvature of space-time predicted by Einstein's general theory of relativity firsthand. First of all, you approach the speed of light as you fall into the black hole. So the faster you move through space, the slower you move through time. Furthermore, as you fall, there are things that have been falling in front of you that have experienced an even greater time dilation than you have. So if you are able to look forward toward the black hole, you see every object that has fallen into it in the past. And then, if you look backwards, you'll be able to see everything that will ever fall into the black hole behind you. So the upshot is, you'll get to see the entire history of that spot in the universe simultaneously, from the Big Bang all the way into the distant future. That's absolutely fascinating. But astrophysicists still don't have all the answers. These theories are still theories, and they admitted that black holes are still a big question. Always the same question: what happens when you fall into a black hole? Do you glide right through and live a normal life thanks to a reality that's strangely observer dependent? Or do you approach the black hole's horizon only to collide with a deadly firewall? No one knows the answer. And it's become one of the most contentious questions in fundamental physics. Physicists have spent more than a century trying to reconcile general relativity with quantum mechanics, knowing that eventually one or the other was going to have to give. The solution to the firewall paradox should tell us which, and point the way to an even deeper theory of the universe. But what is exactly the firewall paradox? It's a bit complicated, but we can try to talk about it. When Hawking first developed his theory of Hawking radiation, he felt that information had to be lost as the black hole evaporated. But let's explain what is Hawking radiation. Over time, the mass of the black hole is emitted in a form of radiation and eventually will disappear. This emission of particles, called Hawking radiation, or HR, arises from the concept of virtual particles. These arise in the near vacuum of space as quantum fluctuations in space-time cause the particles to sprout out from vacuum energy, but they usually end up colliding and producing energy. We usually never see them, but in the vicinity of the event horizon, one encounters uncertainty in space-time and virtual particles appear. So one of those virtual particles would be lost past the event horizon, and we would have no way to know anything about it, a violation of unitarity. This is known as the information paradox, but in the 1990s, it was shown that the particle which enters the black hole actually becomes entangled with the event horizon, so information is preserved. The word firewall does not involve a fire such as here on Earth. No oxygen is required. Rather, it refers to a lot of energy being released. There are three physics concepts involved here. The first is based on the equivalence principle of general relativity. Because an observer is in free fall as they cross the black hole's event horizon, the equivalence principle says that there is no detectable difference between free fall and inertial motion. The observer shouldn't feel extreme effects of gravity. The equivalence principle is only applicable in small regions. Tidal effects can also occur. The second concept is based around quantum mechanics and is called unitarity, which conjectures that information that falls into a black hole is not irretrievably lost. But finally, there is the assumption that the physics far away from a black hole obeys the same laws as here on Earth. The laws may fail near the event horizon, or if not there, at the singularity itself. Obviously, we have problems testing this, but it is generally regarded as an inevitable consequence if you describe the universe using general relativity. Joseph Polchinski has put forward the idea that the simplest solution is that the equivalence principle breaks down at the event horizon, thereby giving rise to a firewall. If this theory is wrong, it may help to resolve the problems in reconciling general relativity and quantum mechanics into a theory of quantum gravity, which still to be unequivocally formulated and aspects of which have yet to be experimentally tested in any way. Black holes are involved because they represent the meeting of general relativity and quantum mechanics, as both theories can apply in those regions. A large part of the firewall paradox argument is based around the notion of monogamous quantum entanglement, that is, you can only have one kind of entanglement at a time. Polchinski and others argue that two different kinds of entanglement are needed in order for all three postulates listed above to be true. Since the rules of quantum mechanics don't allow you to have both entanglements, one of the three postulates must be sacrificed. This is the firewall paradox. If the true nature of reality lies hidden somewhere, I think the best place to look is a black hole. It's probably best to look from the outside, so at least until they figure out this whole firewall thing. So, would any of you be interested in traveling through a black hole? I want to know. Thanks for watching, I hope you liked it. Please like, share and subscribe to Section 51. I'll be back really soon. Open your eyes, watch the sky. Live long and prosper.